ACE 111 lecture 6 set 2 flip-flops. Any realistic design is a sequential design, and sequential design by definition need a memory element to store the state of the system. Now, a very common memory element that is used in digital designs is a flip-flop. And a flip-flop, we have the capability of expressing a flip-flop, of course, in System Verilog. Let's go through the syntax and see how this works. Here, we have a module that has a, this is a flip-flop module. It has an input D. It has the output Q, and it has a clock coming to that. And then what happens is that this, as we mentioned last time, the FF is used for sequential, always FF is used for sequential design. And then this is going to be sensitive to the clock. And because, you know, this is sensitive to the positive edge of the clock, we have this command always always underscore flip-flop at positive edge of the clock. Now what happens is that after that we get this D given to the value of the Q, in which case we say Q gets D. Basically, the output gets the value of the input right at the positive edge of the clock. Here is what, if you write this module in Verilog or System Verilog, this is what you get at the end. Actually, you cannot write this module in Verilog because it has the always underscore FF, which is a System Verilog command. But if we write it in System Verilog and you synthesize it to simulation, this is what you get. Now, you could add more signals to your flip-flop. For example, like, you know, in addition to the clock and data coming in, you could have a reset to this flip-flop. So this reset signal may be asynchronous or synchronous. An asynchronous circuit reset means that you could reset the value of the output to a given value, for example, here as 0, if the reset is asserted. You know, no matter if the clock has its positive edge or not, and this is, in this case, this is sensitive to the positive edge of the reset as well. So anytime in the circuit, no matter if the clock has been asserted or not, or is it going through the positive edge or not, as soon as you hit a reset, you're going to reset the value of the output to a given value, in this particular case as 0. Now, we can have synchronous reset. We could also have enable. An enable signal means that this flip-flop is working if it's enabled. If it's not enabled, it's not working. So in this particular case, we have a flip-flop with asynchronous reset, which means that again we have the positive edge of reset like we had last time, but also this Q output gets input or Q gets D if this is enabled. Notice that in the last few slides I've been using this command, just less than equal, or just given to or gets to, and not the equal sign we have done for assignment before. This is something we will be discussing as we go with this lecture, but no, here is just one example of the use case. If the enable signal here is asserted, then the output gets the value of the input. If enable is not asserted, it's not going to happen. Now, we could have other combinations. We could have a resettable flip-flop, which is also enabled. So this is again, if it's reset, then else, if not just else. This is just a So you could also use the single always statement to describe multiple hardware. Here, what we have is, you could have more than just one flip-flop. You could have other flip-flops. For example, here we have one flip-flop here. And one flip-flop here, and we just give the input, the name of the input, output of these units, and at the positive edge of the clock, these assignments are going to happen, and this is going to give to the output the value of the input of each of the flip-flop. So one thing you need to make sure that is, the output of the flip-flop needs to be declared as a register, because it's an internal signal used in the left-hand side of this value. So here, if I have a gets to sign, then this value should be a register. And the begin end constructs is also necessary because we have more than one statement appearing in the always at flip-flop statement. So these are things that you will see on and on. So we have the begin end, and that is going to tell us what is happening in this batch of signals. If you remember from your logic, basic logic course, the memory elements in a circuit could be also a latch. A latch is a memory element that is sensitive to the level of the clock and not to the positive or negative edge of the clock. And in synchronous designs, latches are way less used than the edge-sensitive flip-flops, because they could be hazardous in terms of the timing. It is not unless you have a very specific type of design that uses latches for a specific place. Latches can be hazardous. They often generate warning in your design, and they have to be used by caution. Here is just an example of a latch defined in System Verilog. Again, you see that this output should be a logic, but this is sensitized by clock, not the positive edge of the clock, and there is this command in System Verilog, always latch. Next, we will be discussing more details about blocking and non-blocking assignments, like some of the things we have seen earlier in the class.